Okay, today we are going to calculate the voltage of this right occipital spike, which happens to be followed by a slow wave component. And whenever you measure the voltage of an individual waveform, you want to use a bipolar montage. In this case, we're using a circumferential, also known as a half band montage with occipital focus. So we're putting the occipital electrodes in the middle of the chain, thereby allowing for phase reversals, which is the whole benefit of utilizing a bipolar montage. And whenever you measure the voltage of an individual waveform per AC&S recommendations, you want to use a bipolar montage as opposed to a referential montage. You utilize a referential montage for measuring voltage when you're comparing hemispheric symmetry or asymmetry. So I'm going to look at my scale legend. I'm just going to look at the vertical component. The horizontal component, where it says 1 second, is for measuring the time base. So it's really two different things. The vertical component is for measuring the sensitivity. So I'm going to line up my millimeter ruler and measure the whole expanse of that vertical line. And it looks like it's approximately 9 millimeters. We can see that this distance is equal to 750 microvolts. So for our sensitivity, we're going to set it up like this. Remember that your sensitivity, the default per AC&S guidelines, is 7 microvolts per millimeter. So we're going to keep that format of units. So in this case, we have 750 microvolts over how many millimeters? Well, we measured 9. Then we're just going to reduce that using a calculator. 750 divided by 9 is equal to 83.3, so we'll just say 83 microvolts per millimeter. The 1 is implied, or 83 microvolts per 1 millimeter. The second thing we're going to do is measure this spike component, and we're going to measure the one in the O1, O2 channel. It seems to be higher, so more representative of the spike's amplitude. We'll pick the higher deflection, and we're not going to measure from the peak to the EEG baseline. We're going to actually measure from peak to trough. In this case, it's flipped, right? Because it's O2's in the second input, but that's okay. Everything's otherwise the same. So we're going to start at the peak or trough, depending on how you look at it. We're going to go all the way to the tip of the spike. 1, 2, 3. So I would say that's about 3.5 millimeters. Okay, so we'll start a new box here. So we measured that spike to be 3.5 millimeters. Now what we're going to do is to the right of this, write out our sensitivity. And we've already calculated our sensitivity to be 83 microvolts per millimeter. So 83 microvolts per 1 millimeter, or you can just write millimeter. And it is important to make sure that your units are arranged when you're doing EEG calculations so that the units you're trying to get rid of or convert from are canceled out. In this case, you can see the millimeter is in the numerator here, and the millimeter is in the denominator here. So millimeter divided by millimeter, the units cancel. And then we simply multiply 3.5 times 83. And we get a value of 290.5 microvolts. So this unit was not canceled, so it carries over. And once we multiplied 3.5 by 83, we came up with this right here. What if we wanted to calculate the frequency of this spike, and just the spike component, not the aftergoing slow wave? Well, we're going to utilize our time base for that. And our time base is going to be calculated or derived from the horizontal component of the scale legend. So let's first do that. So we know that from here to here is 1 second. Let's measure how many millimeters that is with our ruler. And a good approximation that I get is 14.9 millimeters. Almost 15, but not quite. So we'll say 14.9 millimeters. Okay. So 14.9 millimeters per 1 second. or per second. That is suspiciously close to a time base that we've all seen of 15 millimeters per second. So likely this time base is 15 millimeters per second. So we can just round to 15 millimeters per second. Okay, so now that we have our time base, let's measure the width of this spike wave. And the width that I get is about 1 millimeter. So the spike is 1 millimeter. So similar to how we calculated the voltage of that spike, we're going to set up our equation. So 1 millimeter, and we're wanting to convert away from that to a unit of seconds. Draw this partition, and then we'll set up our sensitivity. However, in this case, we need to flip the sensitivity so that the 15 is on the bottom. Why is that? That is so the millimeters will cancel out. So we're just flipping it for that very reason. 15 millimeters per second, or per 1 second, the 1 is implied. All right, so millimeters divided by millimeters, those units cancel out. And then we basically have 1 times 1, the 1 is implied here, or you can just say 1 divided by 15, because this is just 1 second. And 1 times 1 is 1. So what is 1 divided by 15? We'll use our calculator, and we get a value of 0.066. All right, that is the duration in seconds. Remember that frequency is the reciprocal of duration, and vice versa. Duration is the reciprocal of frequency. So if we want to find the frequency of this spike, we need to take the reciprocal of the duration of 0.066 seconds. I'm going to move over here to the left side here. We have some more room, draw a little box. So 1 divided by 0.066 will give us our frequency. And that is equal to 15 hertz. Interestingly, as we know, spike waves range from 20 to 70 milliseconds. So if we just look at that duration of 0.066 seconds, kind of going backwards here for a moment, we can convert this to milliseconds easily by moving the decimal place to the right 3 spots. So 1, 2, 3. So that's 0.066 seconds is equivalent to 66 milliseconds. And indeed, 66 milliseconds does fall in the range of 20 to 70 milliseconds, which is what a spike is defined as. So it's a spike, and we calculated the frequency to be 15 hertz, the duration 66 milliseconds. We measured the voltage to be 290.5 microvolts. And that is it. Thank you.